Next problem. Find the Fourier transform of f of x is equal to e power minus a mod x, where a is greater than 0, x lies between minus infinite to plus infinite, and then invert it. So we are going to use inverse Fourier transformation also, right? We know that Fourier transform of f of x is equal to f bar of p, which is equal to 1 by root of 2 pi integral minus infinite to plus infinite e power I px f of x dx. That is equation number 1. Given f of x is equal to e power minus a mod x, that is equation number 2. We know mod x, which is equal to x if x is greater than 0, and minus x if x is less than 0. So this is equation number 3. Now we are going to use 3 in 2, so you will get f of x is equal to e power minus ax if x is greater than 0, it is equal to e power minus a into minus x if x is less than 0. That is e power minus ax if x is greater than 0, e power ax if x is less than 0. That is equation number 4. We are going to use 4 in 1. So first we are going to split the integral, right? So integral in 1 is minus infinite to plus infinite. That is the limit. So first limit is x is less than 0 means minus infinite to 0. X is greater than 0 means 0 to infinite. So we are splitting 1 into 2 integrals. So which is equal to 1 by root 2 pi integral minus infinite to 0 e power I px f of x dx plus 1 by root 2 pi integral 0 to infinity e power I px f of x dx. Now we are going to substitute the values according to equation 4. So 1 by root 2 pi integral minus infinite to plus infinite, right, e power I px in this e power ax, right, dx plus 1 by root 2 pi integral 0 to infinite e power I px in this limit e power minus ax dx. So that is equal to 1 by root 2 pi integral minus infinite to 0, grouping the power of e. So e power, so ip plus a, right, or a plus ip, x is common, take it outside, into dx plus 1 by root 2 pi integral 0 to infinite. Here also we are taking x outside, grouping the power. So e power minus a plus ip into dx. So 1 by root 2 pi integral minus infinite to 0 e power a plus ipx x dx plus 1 by root 2 pi integral 0 to infinite e power, taking that minus outside, a minus ipx dx. That is equal to 1 by root 2 pi. So we know integral e power ax is equal to e power ax by a, right? So using that e power a plus ip x by a plus ip, lower limit minus infinite plus upper limit is 0. Similarly second one plus 1 by root 2 pi e power minus a minus ip x by minus a minus ip. So lower limit 0, upper limit infinite. That is equal to 1 by root 2 pi. Substituting the upper limit e power 0 by a plus ip minus e power minus infinite by a plus ip plus root 2 pi e power minus infinite by minus a minus ip and lower limit e power minus 0 by minus a minus ip. So 1 by root 2 pi, so e power 0 1 by a plus ip, so e power minus infinite 0, right? And the second one 1 by root 2 pi, so first term e power minus infinite 0, e power minus 1 is also, so e power minus 0 is also 1. So minus denominator minus get cancelled, so we will get plus 1 by a minus ip. So 1 by root 2 pi, grouping these two, 1 by a plus ip plus 1 by a minus ip, taking LCM a plus ip and a into a minus ip. So cross multiplying a minus ip plus a plus ip. So you will get 1 by root 2 pi minus ip plus ip get cancelled. So in numerator you will get 2a by, and down a plus b into a minus b formula. So a square, right, a square minus b square, that is ip square, right? Ip square is I square p square, I square is minus 1, so I square minus into minus plus in the denominator. So 1 by root 2 pi 2a by a square plus p square. So therefore f bar of p, numerator 2 and denominator root 2 get cancelled, so you will get root of 2 divided by pi a by a square plus p square. That is equation number 5. So now we are going to invert this first. This is the Fourier transform of e power minus a mod x, right? Now we have to invert it. So inversion. We know inversion formula, Fourier inverse, right? So that is f of x is equal to 1 by root 2 pi integral minus infinite to plus infinite f bar of p e power minus I px dp. That is equation number 6. So using 5 in 6, we will get f of x is equal to 1 by root 2 pi integral minus infinite to plus infinite root 2 divided by pi a by a square plus p square e power minus I px dp. That is equal to 1 by root 2 pi. So root 2 divided by pi into a is constant. Take it outside from the integral. Integral minus infinite to plus infinite e power minus I px by a square plus p square into dp. So therefore f of x is equal to a by pi, right? Integral minus infinite to plus infinite e power minus I px by a square plus p square dp. That is equation number 7. So first we are going to evaluate the integral minus infinite to plus infinite e power I px by a square plus p square dp by using contour integration, right? So first case 1. Suppose x is greater than 0, right? X is greater than 0 means e power minus I px rotates clockwise direction, right? In the previous video, we saw how to evaluate the contour integration and how to take the rotation of e power I px, right? So we are using those ideas here, right? E power minus I px rotates clockwise direction. The integral taken round a semicircle with center at origin and lying below the real axis, right? So the integral over the semicircular arc will tends to 0 as the radius of the arc goes to infinite. This is from the lemma, Jordan's lemma, right? So let f of p which is equal to e power minus I px by p square plus a square. So that is equal to e power minus I px. So splitting the denominator, right, factorizing the denominator, you will get p plus ia into p minus ia. So now first we need to find the pole because we are going to use the residues idea, right, residue theorem, right? So first we need the pole. So to find the pole we have to take the denominator equal to 0, right? So take p plus ia into p minus ia equal to 0. So you will get p is equal to minus ia and r p is equal to ia. There are two poles, one is minus ia and other is ia. Both power is 1, right? P plus ia power 1, p minus ia power 1, correct? So these are all the single poles, right, of f of p. So p is equal to ia is lying above the real line, correct? So I already told you y-axis is considered as a imaginary axis and x-axis is considered as a real axis. So x-axis from minus infinite to plus infinite. Y-axis, so above the x-axis, right? Y-axis is always positive and below the x-axis the y-axis is negative. Same concept we are having. P is equal to ia definitely is a positive number, a positive value. So plus ia, right? That is in the upper side of the real axis, and minus ia is the below the real axis, right? X-axis, real line, that is, right? So the only pole lying inside the closed contour is p is equal to minus ia because the circle is downwards, right? Semicircle with center 0 lying below the real axis. So below the real axis means minus ia is lying inside and plus ia is outside the contour, right? This is the one, right? So integral over the contour minus infinite to plus infinite e power I px by p square plus a square dp, which is equal to, we know from the residue theorem, we are taking minus 2 pi I because direction is reversed, right? Below means it is a reversed direction, right? Minus 2 pi I sum of the residues dipole also inside C, right? So integral minus infinite to plus infinite e power minus I px p square plus a square dp is equal to minus 2 pi I. Only one pole, right? So residue at a pole P is equal to minus Ia. That is equation number 8. So we need to find the residue at the pole P is equal to minus Ia. We know residue of f of P at pole P is equal to minus Ia of order 1, single pole. We are using the formula. So residue of f of P at P is equal to minus A, which is equal to minus Ia is equal to limit P tends to minus Ia, P minus Ia into f of P. So that is limit P tends to minus Ia, that is P plus Ia into f of P we know e power I px by P plus Ia into P minus Ia. So P plus Ia in the numerator denominator get cancelled. So you will get limit P tends to minus Ia e power minus I px P minus divided by P minus Ia. So substituting the limit, so you will get e power minus I, instead of P you are putting minus Ia Iax divided by minus Ia, which is equal to e power I minus into minus plus I into I square Ax divided by in denominator minus 2Ia. So I square minus 1, so in the numerator e power minus Ax by minus 2Ia, that is 9. Now we are going to use 9 in 8. Therefore integral minus infinite to plus infinite e power I px p square plus a square dp, which is equal to minus 2 pi I into the residue at the pole P is equal to minus Ia, that is e power minus Ax by minus 2Ia. Minus 2 I get cancelled, so remaining you are having pi e power minus Ax by A. That is equation number 10. Therefore from 7 and 10 f of x is equal to A by pi integral minus infinite to plus infinite e power I px by A square plus p square dp, which is equal to A by pi into pi e power minus Ax by A. So pi get cancelled, A get cancelled, you will get e power minus Ax. So e power minus Ax can be written as e power minus A into mod x. Since x is greater than 0, mod x is x, right? So case 1 is mod x is greater than 0, right? So this is equation number 11. Now we are going to case 2. If x is less than 0, right? Negative means e power minus I px. So x is negative, so already you are having negative, you will get positive in the e power. So this will be counter clockwise, right? So integral taken around the semicircle with center at origin and lying above the real axis, right here. The integral over the semicircular arc with tends to 0 as the radius of the arc goes to infinity. This is from Jordan lemma. So we are going to proceed like above, right? Case 1, f of p is taken as e power minus I px by p square plus a square, which is equal to we will get, as per case 1, we will get two poles of order 1. One is p is equal to minus Ia and another one is p is equal to plus Ia. Now p is equal to plus Ia lying above the real axis, p is equal to minus Ia lying below the real axis. So the only pole lying in the contour, right? In this case p is equal to Ia, right? So we are going to find the residue, right? Before that, using the Cauchy's residues theorem, we know integral minus infinite to plus infinite e power I px by p square plus a square dp is equal to 2 pi I into sum of the residue at the pole inside the C. There is only one pole, so that is equal to 2 pi I residue at pole p is equal to Ia, right? Now we are going to find the residue at pole, right? P is equal to Ia. So Ia, p is equal to Ia is the single pole of order 1. So using the formula residue at f of p, p is equal to Ia, which is equal to limit p tends to Ia. So p minus Ia into f of p, substituting f of p value. So limit p tends to Ia, p minus Ia e power I px by p plus Ia into p minus Ia. P minus Ia in the numerator, p minus Ia in the denominator get cancelled. So you will get limit p tends to Ia e power minus I px by p plus Ia. Substituting the limit, so e power minus I Ia into x, Ia plus Ia. So in the numerator minus I square ax by 2ia in the denominator. So e power I square minus 1 minus into minus plus e power ax by 2ia. That is equation number 13. So using 13 and in 12, so we will get integral minus infinite to plus infinite e power minus ipx by p square plus a square dp is equal to 2 pi I e power ax by 2ia. 2i get cancelled, so you will get pi e power ax by a. 14, equation number 14. Now using 14 in 7, so f of x is equal to a by pi integral minus infinite to plus infinite e power minus ipx by a square plus p square dp, which is equal to a by pi into e power ax by a. So a and pi get cancelled, so you will get e power ax. This can be written as e power minus a into mod x, correct? Because x is less than 0 already, right? So x is less than 0 means mod x value is minus x. So if you are putting mod x value in this case, so minus a into minus x, you will get minus into minus plus e power ax, right? So this can be written as e power minus a mod x. This is equation number 15. From 11 and 15, the final conclusion f of x is equal to e power minus a mod x for all values of x, right? So that is the inversion. Now next problem is like the previous problem, right? Find the Fourier transform of f of x is equal to e power minus mod x. Instead of a, you are a mod x. The previous problem you are having e power minus a mod x. Here you are having e power minus mod x. So put a is equal to 1 in the previous problem. You will get the answer, right? Proceeding like same, right? Put a is equal to 1. Thanks.